Hello everyone, welcome to another session of Big Data tutorial series, and in today's session we'll be talking about Apache Hive. My name is Rajan Chhetri. I am the instructor for this crash course and I'll be sharing my knowledge and experience about Hive today. So first of all, let us start with the agenda first. In today's session we'll be discussing about what exactly is Hive. We'll be talking about the various features of Hive along with the Hive architecture. We'll have a practical demonstration on how to work with the Hive and the various labs on Hive. So first of all, let us start with the session and let us try to understand what exactly is Apache Hive. Now before we discuss Hive, let us first of all understand the problem statement. So here, Hive and related technologies are for handling the big data. Now there is an explosion of data. Terabytes of data is getting generated every day. Now the question is that how do we handle such huge size of data? Standalone systems are not satisfying the requirements for generating the expected output and on time. So as a solution, we have solutions for storing the data, and that is HDFS. HDFS provides us the solution for storing. But what about processing? When we talk about processing, it is MapReduce. MapReduce helps us in parallel processing of the data. But there is a catch. The catch is that when we want to process the data using MapReduce framework, it is Java intensive. It requires a lot of programming efforts as well as understanding the anatomy of MapReduce applications. Now, for a developer, thinking in a MapReduce paradigm can get tricky. So how do we solve such challenges? So as a solution, we have another tool or technology called Apache Hive. Now what exactly is Apache Hive? Let us understand in detail. Now Apache Hive is basically a data warehouse. It allows developers to summarize data. It allows developers to run queries and analyze large datasets by using a SQL-like language called HQL. HQL stands for Hive Query Language. Now, as a storage solution, Hive utilizes HDFS. Hive provides a mechanism to project structure onto the data and query the data using SQL-like language called HiveQL. On top of that, Hive uses MapReduce and HDFS for processing and storage or retrieval of the data. Well, basically, in simple words, we can say that Hive is basically a SQL-like tool which we can use for easing our analysis or data analytics. So whatever SQL-like statements we execute using the Hive tool are basically converted into a MapReduce application. Now there are various features of Hive that makes it more demanding and more appealing for data analysis. Well, when we work on Hive, basically, Hive relies on HDFS for storing the data. But what about the schema? So when we talk about schema or the tables, for schema or the table management, Hive utilizes a metadata store or a mega store, or in simple words, it relies on an external Rdbms. Hive is designed for OLAP, or you can say online analytical processing. Hive is not designed keeping OLTP in mind. Hive cannot be used for transaction processing because of its latencies. As I said earlier, Hive also provides the SQL-like language for querying the data. Hive is fast, it is scalable, as well as it is extensible. Now, when I say extensible, it basically means that we can integrate Java application inside the Hive application with the help of a concept called user-defined functions. Now, Hive is scalable because of its Hadoop underlying structure. or architecture, because Hadoop by its nature is scalable, so it gives the same feature to the Hive. Now, because of parallel processing, it is fast. Now, Hive can be used for various purposes, such as it can be used for the ETL process, which is extract, transform, and load. Hive because of SQL-like language, it provides you capabilities of querying and analyzing the data. Hive works on top of Hadoop, that's why it provides you the capability to handle the large datasets. Apart from that, it has the similar functions of an Rdbms, such as filters, joins, grouping, etc. Now, there are various use cases where we are not supposed to use Hive. Hive should only be used for data which is big in size, or it is only should be used for big data. Hive should not be used for data which does not process GBase, or in simple words, if the data fits inside a single disk, then we should not be using Hive for processing such data, because traditional RDBMS can process that data easily. Hive is mostly suited for processing structured and semi-structured data. If we do not have access to the schema of the data, then Hive is not recommended to be used. We should not be using Hive if we need response in seconds, or you can say for low latency applications, we should not be using Hive. So, as a summary, I would say here that if the RDBMS is solving your challenges, then you should not be investing your time on Hive. Now, Hive is very similar to RDBMS, as I mentioned earlier. Hive has so much similarity that in case if you're already familiar with the Rdbms SQL, then you can easily understand the Hive queries. It is based on the SQL 92 framework, which is the standard framework for the SQL-like languages. Now there are various differences in the working of a Hive as well as working of a RDBMS basically. Now, the differences are like the RDBMS works on a single system architecture, on a standalone architecture, whereas Hive executes on top of Hadoop, which makes or which enables the distributed processing. Now, because Hive works on top of Hadoop, it enables Hive to scale to handle huge datasets that are so large that the traditional systems would fail to handle. So when we execute the Hive queries via Hive shell or Hive interface, the internal execution is done or is handled via a series of automatically generated MapReduce jobs. Now, now there is a difference in usage of Hive compared to RDBMS. RDBMS is basically an OLTP system, which basically means read many times and write many times. Updations are allowed. Whereas Hive is based on read, write once, and read many times. Unlike RDBMS, you cannot perform record level updates or deletes or insertions. Now, there are some advantages of working with Hive on top of MapReduce. So, let us understand some advantages here. So, when you work on a MapReduce application for processing your data, then it is important for you to understand the internals of the Hadoop framework. Whereas, if you are a Hive developer, the engineers or the Hive developer will only require the SQL knowledge to get started with the data analysis without involving in the internals of the Hadoop framework. Let us understand the Apache Hive architecture. Let us understand the major components of the Hive architecture one by one. Now, the very first component that we'll be discussing here is the user interface. User interface allows you to submit a query. process the instructions, and manage them. The command line interface, which we call CLI basically, and along with that, we have one more interface called Web UI. It allows external users to connect with the Hive. Now, if we talk about the second component of Hive architecture, that is Metastore. As the name suggests, the Metastore holds the metadata. It is the data about the database. It is the information about the database. It contains information such as schema and the location of the tables. It also stores the partition metadata present on the traditional relational database. It allows you to monitor the distributed data in the cluster. Apart from that, it tracks the data, replicates it, and provides the backup. Now let us talk about the third component, which is the driver, which is one of the most important and the major component of the Hive architecture. Now, driver is the part of the process engine that receives the Hive QL statements. The driver creates sessions to execute the statement, and it also monitors the lifecycle of the Hive application. It also stores the metadata which is generated during the execution of the Hive query. If we talk about the compiler now, so compiler is also a part of Hive QL process engine. Now the working of the compiler is basically it is responsible for converting the query into a MapReduce input. Now it involves certain technical aspects such as AST, which stands for Abstract Syntax Tree. Apart from that, it also follows the DAG, which stands for Directed Acyclic Graph. Now the next component that we're talking here about is optimizer. Optimizer is responsible for the transformation in the execution plan. It is responsible for optimizing the DAG, which stands for Directed Acyclic Graph, which basically includes the workflow of the execution. So for achieving the better performance, it basically splits the task into smaller subtasks. Now the next component is executor. Executor is responsible for scheduling or pipelines. So the responsibility of executor is to look after the task which will be executing during the execution process. Let us describe all the components in detail one by one. So, user interface. User interface is basically an interface which is given to the user for interacting with the Hive environment or Hive architecture. User interface is responsible for receiving the inputs from the user in terms of commands or the Hive QL. Metastore. Metastore is basically a repository where the information is stored about the tables and the schemas or the databases. Metastore is generally represented via any Rdbms. So generally we'll be seeing generally MariaDB or MySQL. HiveQL process engine is similar to the SQL for querying on schema info on the Metastore. So HiveQL process engine relies on the Metastore for retrieving the information about the job execution. Now let us understand the execution engine. Execution engine comes into the picture after the compilation and optimization steps. It executes the execution plan created by the compiler in order of their dependencies using Hadoop. It is a part of your HiveQL process engine and is responsible for generating the sequence of MapReduce jobs. Now the next component is HDFS. HDFS is Hadoop Distributed File System, which acts as a storage layer for storing the data on which the computations will be performed by the MapReduce application and generated from the HiveQL queries. Here, we will try to understand the working of a Hive. Well, if you look at the execution plan, it looks a little tricky, but let us try to make it simpler. So it all starts from a UI or the user interface. Using the user interface, the developer executes the HiveQL or the query HQL query language. Now the user interface calls the execute interface to the driver. It basically means that the request is sent from the UI to the driver. Now in the next step, the driver accepts the query and creates a session handle for the query. It's basically the information about who is the client and where to send the response. After that, it passes the query to the compiler. The reason for that is for generating the execution plan. Then the compiler sends the metadata request to the Metastore, because whenever we execute the query, we have no information about where the data is, and that's why the data is fetched from the Metastore. The Metastore basically receives the request and sends the metadata to the compiler to process the data. Then the compiler uses this metadata for performing type checking and semantic analysis on the expression in the query tree. A query tree is basically the component-based structural section of the query. The compiler then generates the execution plan, and technically we call it DAG or directed acyclic graph. Now for a MapReduce job, the plan contains the map operator trees and reduce operator trees. It basically means that this will contain the execution for the mapper and execution for the reducer. In the next step, the compiler then sends the generated execution plan to the driver. Now the driver knows exactly how to execute the job. After receiving the execution plan from the compiler, driver sends the execution plan to the execution engine for executing the plan. The execution engine then sends these stages of DAG to appropriate components. For each task, either mapper or reducer, the deserializer associated with the table or intermediate output is used in order to read and rows from the HDFS files. Once the output gets generated, it is then written to HDFS temporary file through the serializer, which basically is a MapReduce anatomy. These temporary HDFS files are then used to provide data to the subsequent MapReduce stages of the plan as per the directed acyclic graph. Now for the queries, the execution engine reads the content of the temporary files directly from HDFS as part of a fetch call from the driver. The driver then sends results to the Hive interface ultimately. So as a summary, we understood that it all starts from the UI. The request goes to the driver requests for the metadata to the compiler fetches the metadata from the Metastore and then sends it back to the driver prepares the execution plan and sends it to the execution engine, and then execution engine follows the MapReduce lifecycle to generate the expected or the output. I hope this is understood how the working of Hive works. Let us discuss about the Hive data types. Hadoop supports various data types for defining columns or field types in Hive tables. So in this section, we will understand what are the various data types with detailed examples here. Now all the data types in Hive are classified into four types. One is column type, literals, null values, and complex types. Let us understand these data types one by one. Integral types. In simple words, we can call them integers or the whole numbers. Now the numbers are basically represented by various data types here, such as small int, tiny int, big int, and int. The smallest one is tiny int, and the sequence goes like small int, and big int. They vary according to their capacity and the memory occupancy. The second data type is string types. String type is for containing the alphabetical data or alphanumeric data. Now, there are two data types here. One is varchar and second is char. Any data which is enclosed in single quotes or double quotes can be represented using string type. Now the third is timestamp. Timestamp supports unique timestamps with optional nanosecond precision. And now the next is dates. These date type data is represented in year, month, and day format. Then we have floating point types. Floating point types are for representing the numbers with decimal points. We have decimal type as well. Decimal type is similar to floating point but with a higher range. Complex types. Complex types are further classified into arrays, maps, and structs. So an array is an ordered collection of similar types of fields that are indexable using zero-based integers. These are just like arrays in Java. Maps. Maps are unordered collection of key-value pairs or primitive types. Structures. Struct is a collection of named fields. This field may be of various types. It is similar to structs in C programming language. Now let us start with a practical demonstration on Hive and let us try to understand how to work on Hive using the Hive QL language. For this, I'll be using the Cloudera distribution for running the Hive. So here you can see the virtual machine. This is from Cloudera. It is freely downloadable from cloudera.com. I'll be using this virtual machine for demonstrating how to work on the Hive. So the very first step is to open the terminal and type Hive. Now we'll be using the CLI tool here, which is the command line interface tool for working with the Hive. So here we have entered into the Hive prompt here. This is the Hive shell. So let us start with some basic commands of Hive and let us find the similarities in Hive and Rdbms. Now the very first thing we'll be doing is to check for the existing databases. So for that, we'll be using the command here called show databases. Right now you can see that there are no databases available as of now, except the default one here. So step one, what we'll be doing basically in the very first lab, in the very first demonstration, we will be creating a database in Hive. For that, we'll be using the command here called create database upGrad DB. Please make sure that every command should be, or every query should be terminating with a semicolon. Here you can see that it says OK, which means the command or the query has successfully executed. Let us verify by listing the list of existing databases by using the command show databases. So here we can see that the database has been created successfully. In the next step, we will enter into the database or we will select the database of GradDB. For that, we'll be using the command called use upGrad DB. Use is for selecting the database or making a particular database as the current database. Now the next step is to work on the tables. Now before we work on the table, we must have data in the HDFS. So I have prepared some sample data with me. So let me first of all make you all familiar with the data here. And for that, I'm using another terminal here, and the data is actually placed in the desktop inside the Hive DS directory. Now this directory is created by me and it has got some files in it. So here you can see that there are three files there: departments.txt, employees.txt, and students.txt. Before we push this data into the cluster, first of all, let us have a basic view of what these files contain. For that, I'll be using the cat command. So I've got two lines here. With one is the ID and second is the profession, which is electrician or plumber. Let us check employees.txt. We can see the employees.txt here. And let us check students. So here you can see I've got some student details with me. So probably it is pretty easy to determine that the very first value is the ID and the second is basically the title. Now the next thing is to observe here is what is the delimiter between the two values, and the answer is comma. Comma is the delimiter between any value here or any row here. So what we'll be doing, we will be creating the tables for this data. Let us push these files into the cluster first of all. So before we create tables in Hive, we must ensure that the data is present on the HDFS. In order to do that, let us create a directory in HDFS. HDFS dfs -mkdir / hive input. So I'll be using this directory for storing all these three files. So here I'm using the mkdir command for creating the directory. Let us push all the three files into the Hive input directory. And for that, we'll be using the command hdfs dfs-put departments.txt / hive input. The syntax which is followed here is -put space name of the file in the local system space the path in the HDFS cluster. We will repeat the same command for the other files: hdfs dfs-put employees.txt / hive input. We'll do it one more time: hdfs dfs-put students.txt / hive input. Let us verify whether the files are present in the cluster or not. And for that, we'll be executing hdfs dfs-ls hive input. So this confirms that the files that we pushed from the local system into the cluster have been successfully stored. We'll be using this data which is present or lying in HDFS for creating the tables in Hive. So let us start with the create table command here. Create table students ID int, and I'll just call it, let's say, name string. All right. So this is not the complete query. So I'll just explain you one by one here. So the command for the query for creating the table is create space table space students. Then you have to specify the column details here. So here I've got two columns with me: ID, which is of integer type, and name, which is of string type. Now in the next step, you have to specify the delimiter in your data. So the delimiter in your data or in the file is comma. So for that, we'll write row format delimited fields terminated by and the symbol. Now here, I would like to bring attention to the command here, which is used for specifying the delimiter in the data. So in the file, you can see here in any given line or in any given record, the values are separated by comma. For specifying the delimiter, we write row format delimited fields terminated by comma. Make sure the query ends with a semicolon. So here we can see that the table has been successfully created. Now let us verify the table existence. For that, we will write show tables. So here you can see students have been successfully created. Now we will repeat the same process for the other data. Create table employees. So I'll just call it, let's say, department ID and emp name string row format delimited fields terminated by comma. We will repeat the same process for the other table. Create table departments, department ID and department name string row format delimited fields terminated by comma. Let us verify all the tables by executing show tables here. So after executing the show tables, we can see here we have created three tables here: departments, employees, and students. Now the next process is to load the data in these tables. If I try to display the data, you can see here that there is no data in any of the table. So in the next step, we will learn how to load the data in table. And for loading the data in the table, we'll follow the command here, load data in path. And here you have to specify the path of your cluster. So once again, I'm repeating here, load data in path space, the path in your cluster. So in my case, it is /hive input /departments.txt. Now, in which table you want to load this data? So I would like to load this data into table departments. So here you can see that I'm loading the data departments.txt present in the Hive input directory inside cluster inside the table called departments. So here we can see the logs here. It says loading data to table upGradDB.departments. Let us verify if we are able to successfully load the data. Select star from departments. We can see here that the data has been successfully loaded. Let us try the similar commands for the other tables. Load data in path /hive input /employees.txt into table employees. So it has been loaded successfully into the employees table. Let us verify. Select star from employees. So here you can see that we have loaded the data in the employees. Let us follow the same process. Load data in path / hive input / students.txt into table students. Select star from students, and here you can see that the data has been loaded into students. Now, if we want to remove the table, right? So we have got select star from departments, select star from employees, select star from students. So till now you have learned that how to prepare the data for Hive, how to create the tables, how to create the databases, how to select the databases, and how to load the data inside the table. If you want to remove the table, you can use the command called drop table students. If you execute the following command, it is going to drop the table. If I show you the existing tables, you can notice here, you can observe here that the students table is not present. Let us recreate the students table, and for that we'll be following this command here, and then we will load the data into the students. Alright, so here you can see that there is an error here. It says that invalid path. Now what does it mean basically? It means that once we load the data from the HDFS into the Hive table, the data is basically removed from its original location. So you can see here there is no file present. We will push the file once again, and now we will load the data once again. So here you can see that after pushing the data from the local file system into the HDFS cluster, I'm able to load the data into the table. Let us verify students. So here you can see I'm able to see the data of students. What if I want to do certain filtration on the data? So let's say I want to see the information of the students whose age or ID is greater than, let's say, 11. So select star from students where ID is greater than 11. So you can see here the filtration is working exactly as expected. Let us try some more complex commands here. Select star from employees. So this is the employee data, and this is the schema. So you can see here it is the schema information. It means it is the metadata of your table called employees. So here department ID is this column and EMP name is this column. Suppose if we want to extract information about how many employees are working in each department. So let us try to do this by the following query. And for this, we'll be using the group by clause. Select department ID, comma, count star from employees group by department ID. So this is the query which uses the grouping clause for grouping the department ID attribute or the column and find the total number of employees present in that particular department. Let us execute the following command. So there is a mistake here. It is employees. So you can see here when we write the complex queries, it is basically launching the MapReduce jobs. If you want to know information about what is happening exactly inside, or if you want to refer to the logs, you can click on this URL by clicking on this URL by pressing the control key. So this is going to present you the information about the currently running. Now let us try to implement a join using Hive. For implementing join, first of all, let us understand the data. So here we have departments table which contains the department ID and the department. Here we have employees table which has got the employee ID and the name of the employee. So here we'll be using the department ID and the employee ID as the common column for joining these two tables. So as an analysis objective, we want to say which employee works in which department. So let us try to implement a join on these two tables. First of all, let us print the schema of these tables. So here we have department. So we have two columns here, department ID and department name. And here we have employees where we have department ID and employee name. Let us write the join query for merging these two tables on a common column. As you can see here, the common column that we'll be using for joining is department ID. Let us write the join query here. So it is going to be select departments dot department ID, comma departments dot department name, comma employees dot emp name. From departments, join employees on departments dot dept id equals to employees dot dept id. So here, this is the complete syntax of writing a join query. You can call it an inner join for merging or combining two tables based on the common attribute, common column called department ID. So in this query, we are trying to fetch the department ID, the department name, employee name from departments, joining the employees tables on the common columns, department ID from departments, and matching it with department ID from employees table. Let us execute the following query, and here you can see that it is trying to convert this query into a MapReduce application. So this query is submitted to the driver. From the driver, it is submitted to the compiler. Compiler requested for the metadata to the Metastore. Metastore returned the metadata, and the compiler sent the same information to the driver. The driver prepared the execution plan and sent the execution plan to the execution engine. Execution engine basically initiates the MapReduce lifecycle. So that is the working of Hive query or Hive QL language. So here you can see that we have received the information, the merging output of the two tables here. We can see that the Hare is from electrician department, whereas Giri and Sham are from plumber department. So that is a sort of basically analytical output. So yeah. So that was the practical demonstration on Hive and usage of Hive for using Hive as a data warehouse infrastructure, and which is built on top of Hadoop, and it is utilizing the underlying capabilities of the Hadoop. We also saw that Hadoop is also providing its features such as scalability, extensibility, and its fast processing capabilities to the Hive. We also witnessed that Hive uses a HiveQL language which is similar to the SQL for querying and analyzing the data. We also witnessed that Hive uses MapReduce internally to process the data, as well as for storing the data it uses HDFS.